Post-training quantization is fast and easy, but push it down to 4 bits and the accuracy can visibly crumble. So what if, instead of quantizing after the fact, the model could learn to expect low precision while it trains? That is exactly the idea behind QAT, Quantization-Aware training. It simulates the rounding of low precision during training, so the model adjusts its own weights to cope and recovers accuracy that post-training quantization would simply lose. There is one clever trick that makes it all possible, and it is genuinely elegant. Let's dig in. First, let's set QAT against the method it improves on. PTQ quantizes the model after training is already finished. It is cheap and quick, just a little calibration and a conversion pass. But because the model never saw low precision coming, it can lose real accuracy, especially at 4-bit and below where the rounding bites hardest. The weights were tuned for full precision, and now they're being forced onto a coarse grid they never expected. QAT instead simulates quantization while the model is still training. The network experiences the rounding error during learning and adjusts to compensate, so it recovers much of the accuracy PTQ leaves on the table at the cost of an actual training run. It is a bit like how a model learns to shrug off other kinds of noise by seeing that noise during training. So how does QAT actually pull this off? Follow the mechanism one step at a time. During the forward pass, insert fake quantization operations. These round the weights and activations onto the exact low-bit grid that deployment would use, so the model runs for that moment as if it were already quantized. The weights themselves are still stored in full precision under the hood, but every forward pass sees the rounded versions. Because of that, the model actually experiences the rounding error as it computes. Its loss now reflects how it will really behave once quantized, instead of pretending every number stays perfectly precise the whole way through. Here is the clever trick. Rounding has a flat, essentially zero gradient, which would normally block all learning, since the optimizer would see no slope to follow. So QAT uses the straight-through estimator, quantizing on the way forward but passing gradients backward as if the rounding were simply the identity, which lets training proceed as usual. With gradients flowing again, the weights adjust to tolerate low precision. Over training, the model gradually reshapes itself so that when it is finally quantized for real, the accuracy loss is small and sometimes almost invisible. Strip it down, and 3 ideas capture what QAT really is. It simulates low precision during training, inserting fake quantization so the model sees the rounding it will face at deployment and learns to live with it. It relies on the straight-through estimator to keep learning alive, passing gradients through the rounding as if it were the identity. So training proceeds normally despite that flat gradient. It produces the most accurate low-precision models, often nearly matching the full precision original even at 4-bit or lower, where post-training quantization visibly degrades. The catch is that it needs a full training run with data, a pipeline, and real compute, far more than PTQ's few minutes of calibration. All right, let's lock in the essentials. Quantization-aware training trains a model while simulating low precision, so it learns to be robust and recovers accuracy that post-training quantization would lose. It inserts fake quantization in the forward pass and uses the straight-through estimator to let gradients flow past the non-differentiable rounding step. The payoff is the most accurate low-precision models, nearly matching full precision even at 4-bit or below, exactly where post-training quantization visibly degrades. The cost is a real training run, so the practical rule is simple. Try PTQ first, and reach for QAT when its accuracy loss becomes unacceptable. If this style of explaining AI clicks for you, a whole collection of it is waiting at standarity.com. Come explore it with us.